Let's do a couple more of those. So remember last time we were looking at position versus time graphs, and we said that the slope of these graphs represents the velocity. And so how the slope changes, what is the sign of the slope, can tell us things about what the velocity is doing, and then also what the acceleration is. Let's try one more, just to sort of get us primed back. Let's say that I have a position versus time graph. It looks like this. Is that velocity positive or negative? It's always negative because my slope here is always negative. Is that velocity or is the speed increasing or decreasing? Is it getting faster or slower? It's getting slower because the slope is decreasing, the value of the slope or the magnitude, so it's slowing. And so what is the acceleration? Is it positive, negative, or zero? What do y'all think? I'm hearing all sorts of answers. Remember, when the velocity and the acceleration are in the same direction, it does what? It speeds up, right? The speed increases. When they're in opposite directions, it slows down or the speed decreases. So what is the sign of the acceleration in this case? Sorry, what? It's positive, right? So here I have a positive acceleration because the acceleration has to be the opposite direction of the velocity because it's slowing down. Right? So this graph, the object that's shown by this graph would have a positive acceleration. So slope of a position versus time graph describes the velocity, but there's also acceleration information there as well. Now the slope of a velocity versus time graph, as we said, is equal to the acceleration. Remember also the area under a velocity versus time graph is the distance traveled. We'll work through some example problems in just a bit regarding that. So here in this first graph is the velocity increasing, decreasing, or staying the same. Is the velocity increasing, decreasing, or staying the same? It's increasing, right? That should be easy. It starts here, it goes up here, so the velocity is increased in value. What is the acceleration? Positive, negative, or zero? It's positive. Because what is positive? The slope is positive, right? So the slope of a v versus t graph gives our acceleration. So here I have an increasing velocity, and my slope, or excuse me, my acceleration is positive. I have a positive acceleration. All right. So if I were to draw the x versus t graph, this is something you might have to do on the exam, where I give you one graph and you have to draw the correlating other graph. I give you a v versus t, or I give you an x versus t, and you have to draw the other one. So you should be prepared for that. So for example, here, if I were to draw the x versus t graph, I know that the slope always has to be positive, and the slope has to be increasing, right? Because here, the velocity is always positive, and the velocity is increasing. So how do we draw this graph? Would this graph look like this? We'll do this as a clicker question. Would this graph look like this? Would it look like this? Or would it look like this? So do blue is A, red is B, black is C. What is the position versus time graph that corresponds to this graph going to look like? Is it the blue line A, the red line B, or the black line C? I'm sorry? I want you to click in here. Remember, you can talk to your neighbor about it. Let's see, Deep and Prakash, do y'all have clickers yet? You do? Okay, yeah. Why don't you see me afterwards? We'll read. Huh? It's AA. The frequency is AA. So you hold the power button down until it flashes, and then you press AA. You got this in 3 more seconds. Right. Is anybody missing a clicker today? Oh, okay, looks like we got everybody. Alright. So B is the right answer. It is the red line because I have initially a small positive slope, and then that slope gradually gets more and more positive, increasing. And that's what's happening in this graph. All right, what about this one? Which line is going to represent the position versus time graph? I'll give that one a go. Looking at the second graph, which one represents the position versus time graph for that second one? Here I have a 0 acceleration because the slope is 0, constant velocity. Which one is the position versus time graph? I'll stop at 25. Let's guess if you're not sure. Alright, C is right. The velocity is not changing, so the slope isn't changing. So you should have a position versus time graph that has a constant slope. Alright, let's try this little quick test. Which of these plots is impossible? I'll stop at 20. Very good. Excellent. Let's see, I usually tell a joke when y'all get 100%. I think I told you about the O Street. Okay, I told you that one. What did the fish say when he ran into a concrete wall? Damn. You get it? Yeah. All right. So let's see. Oh wait, no. What did y'all put? B, right? You put B, right? Yeah, it's because you can't be at the same place at 2 times. All right. At 2 places at the same time, and that's what you have at B here. Alright, Park is running slowly in gym class, but then he notices Jenna watching him, so he speeds up to try to impress her. Which of these graphs would represent his motion, or could represent his motion? He runs slowly first, and then he speeds up. Just a few more seconds. I'll stop at, say, 31. Oh goodness, I have another joke for you. Prepare a joke book. I should, yes. How about another potty joke? How's it go? You are sapping my resources here. Why can't you hear a pterodactyl going to the bathroom? Because the P is silent. So y'all put C, right? Yeah, so here the slope is small first, and then it gets bigger. What's another possible answer, actually? Nobody put this one, but it could have been correct as well. B. Not B, because he's going fast, and then he slows down. But what? D could also be a right answer. So here he's going slow, but in the negative direction, and then he speeds up in the negative direction. But everybody put C. That's what was intended, but D could also be a correct answer. All right, guys, so we're going to go into looking more quantitatively, and we'll come back to sort of looking at plots of motion. Looking at plots of motion, how to interpret them, what have you, and that will be a big part of your exam, especially in the multiple choice part, but maybe also in the free response for drawing figures representing certain scenarios in motion. Another big part of your exam will be interpreting graphs, and then also using derivatives to determine the velocity and acceleration of an object. and this will carry over into the next chapter as well. But first, let's just derive the equations of motion. There are only two equations of motion. You should know how to derive them. I could ask you a question on the test, and if you look back at the old exams, you'll find test questions where I just say, derive the equations of motion. And I'll just expect you to regurgitate this back to me. So the equations of motion start with two definitions. This is the first definition, that our acceleration is the first derivative of the velocity function. And so with that, we can say then that dv is equal to a dt. Just rearranging that. And then taking the derivative of both sides, then we find that dv is the integral of a dt. Taking that derivative, the integral of dv is just v. And what's the integral of a dt? If a is independent of t. So here we're dealing with acceleration that is constant, so a does not change. So really what I'm asking then is, what is the integral of dt? It's just t, right? So the integral of a dt then is just going to be at. Most of you are in Calc 1 right now, right? Well, whenever you take an integral, you have to consider the initial conditions as well. And so they call that in Calc 2 an integration constant. So whenever you take an integral, you have to add a constant. This is the integration constant. But in physics, it's just the initial condition. So that's going to be our initial condition for the velocity, which is just going to be v naught. So it's at plus v naught. And so that's going to be our first equation of motion. Usually when I write it, I'll write it like this. V is equal to v naught plus at. All right? And that's the first derivation. So there are really two derivations that you'll be responsible for, and this is the first. It hinges on this definition. So you'll need to know that definition for acceleration. It's the first derivative of the velocity. And then the second hinges on the definition of the velocity, which is the first derivative of the position. Can I go down from here? All right. So it comes from this definition, that our velocity is dx dt. And just like we did before, we can say that dx is equal to v dt. Right? And then we can take the integral of both sides. However, here, unlike in the previous one, v is dependent upon t. So v does change with respect to time. The acceleration was a constant value, so it didn't change with respect to time. But we know that v does change with respect to time. What is the function that describes v of t? So if I have a velocity, a function for velocity with respect to time, what is that function? How does v change with time when I have constant acceleration? Right, it's what we just derived, right? So our velocity as a function of time is equal to whatever our initial condition is plus the acceleration times time. So what we're going to do is we'll take this and we'll plug it in for v, and then we'll take that derivative. That's going to be the integral of v naught plus at times dt. Alright? Am I losing y'all on this? Y'all are okay? Okay, good. Alright, so when I take this integral, I can distribute it out and it'll look like this. Integral of v naught dt plus the integral of at dt. And actually I can take that a, because I know that it's constant, and put it in front there. And then I just do this integral. So it's going to be v naught t. Because v naught is just an initial condition, it doesn't depend upon time, and so I don't have to integrate that. It's just a constant value. Plus a times, what's the integral of t dt? Remember our polynomial, the integral of, how did it go? A t to the n dt is equal to a t to the n plus 1 divided by n plus 1. Is that how we wrote it? Or something like that? Yeah. So what's the integral of t dt? T squared over 2. Right, so it's t to the 1 plus 1 over 1 plus 1. So that's t squared over 2. And then we have to add that integration constant. What is our integration constant going to be in this case? Now in the previous case where we were doing velocity, our integration constant was our initial velocity. What is it in this case? What's our integration constant? What's our initial condition? What is it? It's x naught. Very good. So our integration constant is just going to be x naught. And so the way we'll write this usually is x equals x naught plus v naught t plus 1/2 at squared. Right, so that's our second equation of kinematics. And those are really the only two equations of kinematics. There's a third that you can come up with if you substitute one into the other. If you want to memorize it, that's fine. It might be helpful for you occasionally. But I find that if you just know those two, you can solve, well, you can solve any kinematics equation. And then there's this third one as well that a lot of books give that just comes from substituting one into the other and solving for v squared. All right? Y'all good on that? Make sure you know those derivations. They're pretty simple derivations once you sort of see that they both just start with this this definition. A is d dt, v is dx dt, and then you follow pretty much the same steps. Just solving for v or solving for x, and then of course you have to substitute that in for v. Y'all could do that? I just want you to throw it up on the test. I think it's useful to repeat those things just to help you. All right. I'm going to skip this one. This one is really for the next chapter. I'll try to remember to come back to it, though, because this is actually 2D motion. I meant for it to be in the next chapter. Let's do, we're going to watch a little clip. This is a clip of a drag race. There are 5 or 6 cars that are racing. They're all like big muscle cars, like a Lamborghini, and I think there's a Porsche and a Jaguar. There's a little Subaru going. And then we want to figure out some things about the cars, like we want to think about how far they traveled, what was their final velocity. I think the final velocity is given actually. What is the distance that they travel? What is their acceleration? Things like that. So let's first just watch the clip. It's kind of a cool clip anyway. And then we'll consider the kinematics of it. What's the first thing that we can say? What's that? The distance? So what is the distance? Right, a quarter mile. So when you race cars, right, you typically race like a quarter mile. It seemed like a quarter mile race. So the total distance, I'll call that x, is equal to 1/4 of a mile. And then just for the Lamborghini, they gave a couple of numbers. I don't know if you caught them, but the Lamborghini completed that distance in 10.8 seconds. And it completed it, its final speed was 132.3 miles an hour. Have I ever gone that fast? Have you? Okay. 110 where? Oh, in a minute. All right, so we want to convert these first of all to our metric system, to the MKS system. So quarter mile, we need our conversion factor. As I said on the test, I'll give you any British conversions. But a mile is roughly equal to how many meters, you know? You recall? Right, about 1,600, actually 1,609. All right, so I can convert this to meters. 1 mile, 1,609 meters. And that gives me 402.3 meters. All right, and then our time is at 0.8 seconds. And then we can convert our final speed to meters per second. 1 hour is 3,600 seconds. That's something you should know. A mile, 1,609 meters. So, right, yeah. And then if we can see that our units cancel here, miles with miles, hours with hours, leaving us with meters per second. And then that gives us velocity 59.14 meters per second. Okay, so I want to know a couple of things. Actually, no, I just want to know what is his acceleration. So I want you to take a minute. I want you to find what is his acceleration. And when you get a number, please let me know what it is. I'm just going to write the equations up here. These are the ones we just derived. I'm going to step away from this for just a second. I'll bring it back. Somebody got a number for me for acceleration? Okay, somebody have another number? There are actually two values you can come up with, yeah. Okay, so let's write both of those down. They're both correct and they're both incorrect. So, Prakash, what'd you get? 6.9 meters per second squared. And Josh? Okay. I'll call it 5.48. I think that's what I used. Most of you probably got that second one. Is that correct? Yeah. Well, you can get them two separate ways, right? Because we have two equations, and we have enough known values to use either of them. To get this second one, you said v was equal to v naught plus at, right? And you solve that for a. To get this first one, you say that x is equal to v naught t plus 1/2 at squared. And both of these, by the way, the v naught is 0, so this term goes away. And when you solve this equation, you get this value. All right, let's imagine that we don't know the distance. For the time being, I'm going to leave this out, okay? And for let's go with the second acceleration. I'm going to show you why in just a sec. Let's go ahead and calculate what is the distance that's traveled, and then we'll plot the motion. So go ahead and find the distance that's traveled, given that acceleration, assuming that we don't know the distance. We do know it, but let's assume that we don't. Right, given the 5.48. And then let's find the distance that's traveled. Somebody have a value for me? Courtney, what you got?
322.6.
I got a slightly different answer. Anybody get a slightly different answer? Unless you use 5.5. You did, didn't you?
Huh?
You used 5.5 or 5.4?
I used 5.48.
Somebody get a different answer? Okay, that's what I got too. We're gonna go, I'm not sure, maybe you rounded differently or something. But I got 319.6 meters. Alright, but that's different from what we had found before, right? Because we said that actually this is a quarter-mile distance, so it's about 80 meters over that. Let's try graphing this and we'll see sort of where the problem arises in our assumptions. Does anybody know what the problem is in our assumptions? The initial conditions? No, it is 0. Our x initial is 0. We set that to be 0. And our v naught is 0 as well. The cars are definitely at rest when they start. There's another problem in our assumption. In using these equations, we assume something. What is it that we assume? No, not the circle. What?
Accelerating at a constant rate.
Right, we assume that it's accelerating at a constant rate. And that's clear. That's not the case for these cars. They're not accelerating at a constant rate. So if we draw a v versus t graph for these, I know that for the Lamborghini, that it starts at 0, and it ends at a velocity of 59 meters per second. And if I connect these two, I find that that has a slope, that line has a slope of that lower acceleration, 5.48 meters per second squared. All right, if I just connect those two dots and find the slope of that line, which is going to be 59 over my time, I get 5.48, and that's my slope. However, if I then come back and take the area under this line, which is what we did here, I find that the area under this line is 319.6 meters, right, which is smaller. Now, Prakash, when he did this, he did it slightly differently. He said, I'm going to start out assuming that this distance, or the area under this graph, is our 402.3. But then he has a problem because then his final velocity is what? Bigger or smaller than the actual final velocity? It's bigger, right? So that's a problem as well. We didn't see that, but if we took that acceleration, we would find that the final velocity of the car was not the 59 meters per second. It's some higher value. Okay. So in reality, we have something. Let me get rid of that. In reality, we have one of 3 possible scenarios, and I want you to tell me what it is. Is the actual graph, like the blue line that I've drawn here, is it like this, or is it like this? All right, so we'll do A, B, C. Is it the black line, the blue line, or the red line? The actual V versus T graph. The black, blue, or red line. All right, I'm going to stop at 45. 45. Okay, looks like we're split sort of between the black and the red. The line that's correct will give us a longer distance because it's not the blue line, as we've already shown, because the blue line gives us a distance of 319.6 meters. But we know for sure that this is a quarter-mile track, and a quarter-mile track is a little more than 400 meters, right? So we know that our distance is wrong. So we have to have a velocity versus time graph that begins and ends at the appropriate velocities, but has our car traveling a longer distance than 319.6 meters. So which of those gives us that? Is it the black or the red? So you've already said that it's not B. So is it A or C? Yeah, I'm going to stop at 35. 35. A is right. All right, the black line is correct because the area under the black line is greater than the area under the blue line. So that area is going to be 402 meters or whatever it is. It also sort of makes sense when you think about it, because is it harder for a car to accelerate at low speeds or at high speeds? It's easier, right? I mean, it's easier for a car to accelerate at low speeds, right? Once it gets going faster and faster, there's a limit to how fast it can go. And so once it gets up to a high speed, its rate of acceleration is going to begin to decrease. And that's what happens here. See, I have a big acceleration initially, and then that acceleration gradually gets slower as it begins to reach its maximum speed, whatever that maximum speed might be, 130 miles an hour or whatever. I don't. How fast can a Lamborghini go? Do y'all know?
That one could go, I think, 220.
Seriously?
Yeah.
Okay. But it gets harder to go faster when you get up to those faster speeds. Like it is more difficult, just because you begin to lose energy, and just at higher speeds requires more energy to go faster. We'll talk about that in a later chapter. 220?
Yeah, and that's slow compared to some of the other cars they got.
Really? Okay. Wow. Okay. Let's go down. If you have the book, back in the back of the book, page 312, there is an old test question. I think this was from last year's test, actually, for chapter 1 or chapter 2. I want to spend some time in class just working through this. So this is a practice test question for y'all, and I want you to spend some time working it. So now is your time. You spend a few minutes working. I'll give you a little bit of a head start, and then I might start writing some of the answer on the board. So this is on page 312. There's an appendix in the back. Yeah, page 312. An appendix in the back that has old exam questions. That's really good for you to practice for the upcoming exam in a couple weeks, okay? So, but we're going to spend a little bit of time in class just practicing through this. So you'll see some things that we've already seen. Let's do A and B right now. Anybody have the average velocity yet? Twelve what? Okay, let's see. So it's just delta x over delta t. That's going to be between 1 and 3 seconds. So that's 30. This looks like it's 5. So it's the final position minus the initial position over the time, which is 3 minus 1. How do I sig fig? So really just keep one sig fig, but it's going to be 25 over 2, which is 12.5. But keeping proper sig figs, we would just have 10 meters per second. All right, that's just based on our definition of average velocity. You just take your initial and final points off. Why is it 5? Oh, is it actually 6? Let's see. 2. Oh, yeah, you're right. You're right. I was just looking at the graph, but if you actually look at the function, is that what you did as well? Who said? You just eyeballed it. Okay. Yeah, actually, if you want to know the actual position, you can use the function. So that's going to be, to find our final position, it's 2 times 3 squared plus 4 times 3. That's 18 plus 12, which is 30. That's what we put here. But as Tong said, the initial position is actually, and I can find it exactly instead of just estimating from the graph, I can say 2 times 1 squared plus 4 times 1, which is equal to 6. So this would be 30 minus 6 divided by 2, which is 24 over 2, which is actually 12, which would round off to 10. I would accept either. I had intended that you just pull the number off the graph, eyeball it, as you said. It was a pretty good eyeball, actually. But it would actually be 24 over 2. All right? Try the next one, the magnitude and direction of the acceleration at 3 seconds. You'll need to do the derivative. Do y'all have that yet? No? Go ahead and try it out. What is the magnitude and direction of the acceleration at 3 seconds? If you have the position function, you'll need to find the velocity function and then the acceleration function. Do I have it yet for me? No? Give me a minute.
16 meters per second squared.
No, that's not right.
Well,
Positive 4, that's right. So here are my x function is 2t squared plus 4t. And then I want to find the derivative of that. So it's going to be 2 times 2, which is 4, times t to the 2 minus 1, which is just 1, plus 1 times 4, which is 4, times t to the 1 minus 1, which is t to the 0, or just 1. All right, so that's my velocity function. And then if I want to find the acceleration function, it's the derivative of that. It's just going to be 4. So my acceleration is positive 4 meters per second squared. How'd you get 16, Zach?
I would have had to take another direction.
Okay. Okay, no, yeah, don't do that. All right, so the acceleration here is always 4 meters per second squared. What's the initial velocity? You should be able to tell me that just from looking here at these functions. Which value in one of these three functions can tell me the initial velocity? The second one. And which number is the initial velocity? All right, the first 4 or the second 4? The second one, right. So this number is our initial velocity. All right, if you remember back to our equation, it's v equals at plus v naught. So that's our velocity when t equals 0. Or you can imagine, what if I put in t equals 0 here? Then my velocity is going to equal 4. So my initial velocity, v naught, is equal to 4 meters per second. What is the velocity of this object at t equal 3 seconds. And everybody says, what? 16. That's right. Y'all look really excited about it. Appreciate the excitement. So d is equal to v at t equal 3 seconds is equal to 4 times 3 plus 4. This is what you did, Zach, for acceleration? Okay, yeah, that would give you the velocity at 3 seconds. All right, and then how would you find the velocity graphically? Like if I just gave you the graph and you didn't have the function, how would you find it? Here, go ahead and try it out in your book. If you have the book, you can just draw the lines on the graph. All right, so what do you do to find it graphically? You find the what? The slope of the Harley? You'd be right, the tangent line. So I draw a tangent line right here, the best I can, and then I find the slope of it. I'm going to sort of fudge it a little bit, go here and here. Let's see if that gets it right. So that's 40 is my rise, 2 is my run. Hey, that's pretty darn close, actually. So to find graphically, I just find the slope of that tangent line, and the slope equals rise over run, or 40 over 2, just 20 meters per second. Now that's just eyeballing it, but it comes out pretty darn close to the actual velocity. In fact, if we're keeping appropriate sig figs, it would be the same answer, 20. All right, now calculate the total distance traveled. Show me with calculus how you do so. Remember, x is equal to the integral of what? Of what function? The integral of what function gives us the distance traveled? The velocity function. So x is going to be the integral of v dt. And we have a function for the velocity that we've already found. So take the integral of that function. What is that function? It's going to be the same as our position function, right? So the integral of 4t plus 4 dt is just it's like the antiderivative, right? The integral is the antiderivative, so that's going to be 2t squared plus 4t. All right, but you should know that to find the distance, you need to take the integral of the velocity function. Here it was sort of obvious, or maybe it wasn't obvious, but you do need to know that. You might have to do it elsewhere. And then what is the total distance traveled? Somebody tell me. What is it? 17? Well, that's not right, is it? At 3 seconds? Yeah, 3 seconds is 18 plus 12 is 30 meters. And we can find that on the graph here. At this point, I'm at 30 meters. All right. That's just what the question asked. Oh, no, it was the total distance, wasn't it? I'm sorry. Yeah, so the total distance is at 5 seconds. Sorry, so the total distance is 2 times 5 squared plus 4 times 5. It's 50 plus 20 is 70. Is that what you said, Tom? Yeah. And then finally, sketch the velocity versus time graph. So what does the velocity versus time graph look like for this function? What does it look like, y'all? Is it a straight or curved line? It's a straight line, right? Is the line going up or going down? It's going up. So my line's going to look like that. It actually has a slope equal to 4, because that's my acceleration. A slope equal to positive 4. The acceleration is unchanging, so the slope of that line is unchanging. All right, that's a good example of what you might see in terms of just 1D motion. I doubt that we'll get into actual 2D motion for the next exam. We'll probably get into vectors, but not 2D motion. That will come on the second exam. All right. Something like this you should be able to do in under 10 minutes on the exam. You'll have an hour and 10 minutes for the exam. I usually like to come in early for the exam. So, but you have 4 to 6 of these, and then you have 15 multiple choice. You can't dilly-dally too long. Okay, you have a great weekend. Doing whatever it is that you said you were going to be doing, or didn't say as it was.